Hello, everybody. Welcome to OpenCV Weekly Webinar. Today, we have Brandon Miner, who is the CEO of Tangram Vision, with us. And we are going to talk about sensors for sensors. This is the second part of the series. We had a very lively discussion last time about various kinds of sensors in a car. And we will continue that discussion, something about calibration, etc., in this webinar. And also with us is Phil Nelson. As always, he's the content manager at OpenCV. Hi, Phil.
Hey, everybody. As a reminder, at the end of the webinar, we will be doing a Q&A with the audience. Please use Zoom's Q&A functionality to ask your question at any time during the presentation or discussion, and we'll answer as many as we can at the end of the webinar.
That's great. And we will also have a question at the end of the webinar. And if you answer that question, the first person who answers that question correctly receives an Oak One. So today's prize is Oak One. That's OpenCV AI kit without the depth version, but it's still a very powerful camera, smart camera that you can program using Python. So that's what we will give away. So watch out for the question. Most of the questions, most of the time we ask something that has been presented in the presentation. So keep your eyes open. Now, let's welcome Brandon, and let's start with an introduction. Brandon, could you introduce yourself, just a little bit of your background before we dive into the slides?
Sure. Hi, everybody. My name is Brandon Miner. I'm the CEO of Tangram Vision. We're doing DevOps for perception. So, what that kind of means is robots and vision-enabled devices are complicated machines, and getting the data plumbing right is important, something we'll talk about today. So my personal background, I did a lot of self-driving car research in my PhD, left my PhD to do computer vision work. And calibration has really become one of my passions, which is not common. Again, I don't think anybody can really say that. So we'll dive into it today. I'm pretty excited for it.
That's great. So let's get started with the slides. We have some very interesting discussion. We are going to have a very interesting discussion about sensors and how calibration works, etc.
Yeah. So let me share my screen here. Get this going. Good to go?
Yep.
All right.
It's showing 2 slides.
It is. There we go.
Great. Now it looks fantastic.
How does that look? Yep.
Yeah.
That's what happens when you're on Linux. All right. So yeah, let's dive into it. Sensors for your sensors part 2. This is part 2, which means there was a first part, which was my first talk. You could say they're artificially connected. That's fine. But I think they meld together pretty solidly. So just to recap of part 1, right? We asked the questions, why are there so many freaking sensors? And we started with this car. So, we had radar, we had Lidar, we had cameras, we had ultrasound. We probably have a couple of IMUs on there. And these systems are so complicated, but there's no turning back from it at this point, right? They all compensate for each other. They all have a role. They're all important. So having them all there is a necessity. We need more out of our machines. We need more sensors. And we took that, we took a electromagnetic view of these things and saw exactly why these sensors compensate for one another. You have visible, then you have the ultraviolet, then you have the infrared that give more information out of the visible. Then you have radar and Lidar, which compensate for those as well through distance and time. You have to stitch all these together to make a machine. So, the moral of that talk was there is really no going back from this. Sensors are so ubiquitous and cheap and powerful at this point that there is no downside to having more sensors on your machine other than trying to stitch them together, which is still a huge pain in the sense.
Brandon, do you have a blown up version, a bigger version of the picture on the left?
I don't, but I can do that artificially. Right. Yeah.
Because that's a very important slide. And you can see here that RGB camera sensors, they have different capabilities, different range, different resolution, etc. And there are other sensors also, right? This one gives a very clear picture. The light blue is the camera sensor. And you can see that it does cover a lot of areas, but it doesn't go far enough. The resolution of the camera at that point becomes really small, right? Or you may have to use sometimes, for example, in Tesla, they use from the same, approximately the same location, they use two different cameras. One is wide angle and one is a very small angle, right? So, and then you can see that radar and Lidar, they go farther away. And then there are things like ultrasonic sensors, which are literally, they have a very short range, but they are to make sure that you don't bump into, where you're backing up and things like that. You don't bump into stuff. So all these sensors are absolutely necessary. There is no way of getting around them. So what do we do? And these sensors need to work together. They need to be aligned together. The output need to be registered with each other. Yeah.
Yeah, the sensor fusion problem is not going away.
Yeah.
I mean, if any of you live in San Francisco, when I'm in San Francisco, I see at least 3 self-driving cars a day, parked or unparked, and it's easy to see, exactly what they're trying to get away with here. They're huge machines. The computation is enormous.
Yeah, and Elon Musk says that cameras are enough, but there are conditions like fog and other things where you want something else. You need a collection of sensors, right? And I don't even know whether the current set of sensors would be enough for full autonomy. You do need something that works in a lot of conditions.
Mm-hmm. Which again, see the first talk, we dive into it quite a bit. So let's see, oh, I did a bad thing. Nope, this is what happens. All right, here we go. I have learned. So that was first talk. We were just talking about how many sensors there are and why they're all actually needed. But today we're going to transition to the bigger problem, in my opinion, which is stitching them all together, right? This, what Satya just said, the sensor fusion problem, which has not been solved as of yet. So, data plumbing, in my opinion, stitching these all together is actually a problem of calibration. This is why I'm so excited about the problem of calibration. And I say problem because, again, it has not been solved yet, to my knowledge. Calibration really gives you the tools necessary to understand your data at a fundamental level, no matter the sensor it's coming from. So, say the cameras on that car, we're going to need to know how light bends through the lens. That's called its intrinsics, exactly the profile of the camera itself. We need to know the extrinsics, which is its relation to other sensors on the machine. Extrinsics can be spatial. You can have 2 sensors distance, you need to know how to register them, but it could also be temporal, right? You have connections between these sensors, and you need to know exactly how they differ in time so that you can better judge their performance. And then intrinsics and extrinsics together lead to calibration validation. So what that really means is you're going through time and you need to make sure that the calibration you had at one point is the same at another point, is the same at another point. And if that's not true, then your system as you've designed it will mess up. Like, you don't have the same power that you had before to do all these things because your understanding of your machine has changed, right? So it's this understanding that calibration gives you, and why I think it's such a valuable tool, such an underestimated tool in industry.
And just to give a little bit more flavor on what these intrinsics are, because most people are familiar with a camera, we can pick the example of a camera. Like for a camera, the intrinsics would be the focal length of the camera, even though, the camera says, the manufacturer says that the focal length is such and such. That may not be the exact focal length. They may be off by some percentage. So, and for these kinds of applications, we need to be 100% sure that we are as close, because we are using these cameras not for photography, right? We are using it as a sensor. We need to estimate things, some data from that thing. So we need to make sure that all the intrinsics are perfect. So focal length is one intrinsic. The second thing could be that the plane of the camera, it may not be centered. It may not be centered at the exact center pixel. So that offset we need to account for. And then the lens that we are using, it may be causing some distortion. So there are a lot of lens distortion parameters that come in when we are doing camera intrinsics. So those are the high level camera intrinsics. And then if you talk about extrinsics, we also need to know how this camera is connected to other cameras. For example, if you have a stereo pair, what is the relationship of one camera with respect to the other? So you need the rotation and the translation between these two cameras. So we could say that those are the extrinsics of the camera. It is the relationship of the camera with respect to some global or the world coordinates. So that's roughly, but obviously these intrinsics and extrinsics have different meanings when we are talking about different sensors.
Mm-hmm.
Yeah. Okay.
And we'll actually get into that in a little bit, trying to figure out exactly what this means for different sensors. But the story is the same for sensor modalities. You need to understand how it works internally, how it relates externally, and how it changes over time.
Yep.
So, that brings us to pipelines. There are so many data types and so many ways to move data around that this actually becomes an engineering problem. And when our perception pipeline explodes, who do we call? Data in so many ways has analogies to plumbing, right? You have pipelines, you have data flow, and engineers can be considered the plumbers of such things, but where are the data plumbers? The problem is that position doesn't really exist in industry. Calibration engineers are very few and far between in industry. You can find a little bit more in academia, but the study and implementation of these data pipelines for sensors and perception is not currently a job. It's not currently a role.
I'd just like to chime in and say how disappointed I am that you missed the opportunity to put Mario on this slide.
I'm a Mario silhouette, and I am sorry, Phil, I have no excuse.
I'll forgive you this time.
I appreciate it. So, that is one of the fascinating questions that I have yet to answer in my time in industry, is like why this isn't more of a big deal. It just seems like a big deal, especially with these sensor systems that are just so complicated. Right now, it takes 50 generalists, to understand this problem. So we'll be digging into that in the rest of the talk.
Is it because of the complexity of what is involved? Because if you want to have a calibration engineer, does it not mean that you need to have solid knowledge about all these different sensors, right? Is it an expertise problem, do you think?
I think it is an experience and expertise problem. But at the same level, I don't think the problem has been contextualized in this way. Because if you're working with a autonomous vehicle, for instance, like an RC car, you might have a Lidar on there, you might have some cameras, but as soon as you understand, as soon as you get the data pipeline going a little bit, you start working on the cooler, higher level stuff.
Yeah.
Right. Because it's the cooler, higher level stuff that you're really building the machine for. But the data pipeline itself still has not been solved, and it turns into a big issue. So I think it's just the conceptualization that's also half of it. Yeah. So that's a great segue. Like, let's talk about how we do this right now. I have illustrated the car of the future as I see in my mind. It's pretty easy. It has a front cam, a back cam, Lidar on the top. I am you. Again, if you're walking through San Francisco, you probably see something a little bit like this, except add 5 more of everything. So let's get into how right now, given the tools we have in industry, we would solve this calibration problem. Awesome. OpenCV provides the first answer. Camera calibration is usually done through the Calibration Dance, aka Zhangs Method. So you'll print out this checkerboard that has known square sizes, known metrics. You move it around and see how, again, light bends, how the checkerboard deforms around this lens. And then at the end of that process, you just let the math run, gives you the parameters, the intrinsics, and then you say, is it good enough? It's good enough. And you're done. It's popular
Checkerboard has to be real flat too. Real
it has to
flat.
be really flat, yes. Because what you're really doing is understanding the object space, you know, exactly how these things are lined up metrically in Euclidean space versus the way the light is affected in the lens. So if you don't have that exact and flat, you will get wrong parameters, but assuming that everything is good, you know, this method is actually one of the best, one of the simplest. It's popular for its ease of use. And you can get the intrinsics, as Xiaotiu was talking about, you know, the focal length, the principal point, the center offset, and the extrinsics. You know, you can have two cameras and figure out their relation to one another in one process. So this is actually a super cool, simple method that you can find in OpenCV. You can also find it in the ROS library. It works really well for what we're doing.
Right. And I mean, if you're trying to build something industrial, I would advise that you also look at the Charuko pattern, which is, you know, these black regions, they replace it with Aruko kind of markers. And so that pattern is more stable. It produces better results. And if you want to do something cool, you can also use the circular patterns that's also part of OpenCV. That looks very cool that, oh, you're not using a checkerboard. Look, I'm using these circles. And it works very well as well. So those are the two things that you can check out.
I'm pretty familiar with circles. I would recommend Charuko, though. It's a pretty powerful tool. But you know, at the very end of the day, if you have a checkerboard, it works, which is one of the magic. So we have cameras. We have our cameras. Now we have to use the information we had in our cameras to inform our Lidar calibration. And Lidar intrinsics are a bit different. So, you know, they also they're bending light. They're figuring out the reflection of the light. But it has to be in reference not to, you know, light and dark patterns, but in reference to distance, to metrics. So what you do for Lidar calibration is actually find a flat plane. You can identify a flat plane and register it against the beam reflection that you have from the Lidar. So from most factory calibrated Lidar, it'll be pretty close, but you won't have it like perfectly flat. And what you want to do with the intrinsics calibration of a Lidar is figure out how to make your beams perfectly flat, you know, or perfectly shaped to your calibration target. But really that's it. I mean, getting the spin time and the power down, you're good to go.
But there is also the extrinsic of the LiDAR calibration. The LiDAR needs to be registered with the camera, right? Like on my phone, the phone has a LiDAR, iPhone 12 Pro Max, whatever it is. It has a LiDAR and also cameras. But if you want to texture map the camera data onto the LiDAR data, then you need a perfect registration, right? So for those reasons, you need extrinsic calibration also between your LiDAR and other cameras, maybe other sensors, etc.
That's exactly right. And you use the camera calibration that you found. You inherently have to rely on the camera calibration you found here to inform the LiDAR extrinsics that you find here, right? So these processes build on each other. That's an important point, because for our last sensor on our module, IMU, we probably need to register to both LiDAR and camera. And so now we're relying on the results of both of those calibration processes to find the IMU extrinsics as well. So, you know, just to touch on it a bit, IMU is a bit different. It's a continuous time model. So you move your sensor through time and see how it drifts, how it behaves. IMU intrinsics are the scale and the bias of the motion and the position in space as it moves. And again, in order to really get a handle on this, you need the information from both your LiDAR and your camera to understand your complete system. So we find that, throughout our calibration process for this car, we've actually been building on top of each of these processes, daisy chaining our information one by one, to get to a fully calibrated machine. Right.
And IM user basically sensors that tell you the orientation of a device that they are connected to. Right?
Yeah, that's right. For context, it's the position and the acceleration and rotation.
Right.
Yeah. So they're pretty tricky, but everybody has them in their phones. They're very used.
Yeah.
So we found that what we wanted was this calibration process that stacked on one another and gave us a great picture of our data for this vehicle. But what we got was something very iffy, which you might not have seen. So this is one of the unpredictable things about calibration right now in industry, is that the tools we have basically say that the calibrations we've derived are absolute. It's like, this is the picture of your camera. This is what your LiDAR did. But what it is in reality is that there's a lot of uncertainty that goes through this, both on the data side and the mathematics. So, it could be a blurry camera image. It could be that you misclassified a plane on your LiDAR and it wasn't quite flat. It could be that your IMU just had erratic motion, but whatever it was, that error was baked into your calibration, so that by the end of this daisy chaining of events, what we got is actually very uncertain. We don't actually understand the car.
Right. And actually, the another real world analogy here is, the game of telephone, where you have a series of people and the first person is told something while the others cannot hear it. And the person needs to repeat that sentence to the other person. And you keep doing that after, say, 15 people or so, it's a completely different message. What the person said was completely different from what the person in the end got. So when you're trying to calibrate also, if you're calibrating these things independently or two at a time, let's say you are calibrating a stereo pair, but there are 100 sensors or 100 cameras in the scene, and you're doing two at a time, then the errors, very small errors, they will percolate, and you will see that, oh, it doesn't make sense. The 100 camera system is not the same as calibrating the 100 camera system is not the same as calibrating 2 cameras at a time, right? So you need to have a global calibration in some sense, so that all of these errors are taken into account while it calibrates everything, right? So it's almost like the instructor in the telephone game. If they tell you independently the same phrase, then even if it is noisy, you can actually piece together all the information that people have independently heard, and then come up with what the actual probably is, right? Instead of this serial game of telephone.
Yeah, that's exactly right. And that is, that is coming up, is what I meant to say. Excellent point. But right now, that's not quite the case. Like I said before, there's a lot of instance in academia where this is true, where you can find larger tools to get this out. But right now for industry, it's a different thing. Like, every sensor is still calibrated one at a time. You're dependent on the last results. This truth and error question becomes really big. And so right now the calibration is patchwork and painful. That's the whole theme. But this patchwork, painful calibration process has not been solved by industry by making calibration better. So instead, what these larger, perception-based products do is that they make compromises other places to avoid the calibration problem entirely. And so you can think of, reducing the feature set, getting rid of some sensors, easy to do, but you're going to restrict your abilities, making difficult demands on the user. So making sure that once it's out in the field, you have to calibrate instead of calibrating, in factory or what have you. Changing the industrial design so that these problems just are less tractable or more tractable. This one is most painful because you've probably been in a year or two of development, and then you're like, we just can't solve this. This is bad. And then the last one is just buying more expensive sensors. Generally, more expensive sensors have understood behavior, which is something you'd like in your machine. So anything to avoid calibrating. It's really anything to avoid calibrating all these sensors. Industry will do. So just
to give some more real world flavor, we have worked with 2 clients recently whose product is ready. They say that the product is ready, except that the calibration takes a long time. The procedure they are using for calibration is painful for the user, so they cannot release the product yet. So this is how important the calibration is. Something, let's say if the calibration takes 5 minutes versus 30 seconds, that's a huge difference, right? And that can stall the development of your product or the release of your product, right? And it's not just the calibration, right? It's actually quite a lot of work to get down a calibration procedure from, say, 5 minutes to less than 30 seconds.
Oh, yeah. And especially if, vision is a big part of your system. If calibration's out and you have users doing it themselves, that's a huge sticking point, because the users aren't necessarily trained in how to do that.
Yep.
Leaving it up to them can be drastic.
Right.
Yeah. That's definitely something Brandon and I had a lot of shared experience with at Occipital.
Yeah.
The calibration app, which I think the current version of it, I actually designed, like, some storyboarded, if memory serves.
And that's a great example of, I think, calibration being done particularly well. It's still a hard process.
Don't let's pat ourselves on the back a little bit.
Yeah, very good. Very good job, us. Yeah. But no, that's a great example. That is, that sensor is relied upon to do some very cool stuff, and users need to know how to do it. It is done. It's done well, but the process getting there took years. So that's just an idea of how complicated this problem is. And that's because we had to do it, right? Again, in industry, if you don't have to, you usually don't. You usually avoid it. It's somebody else's problem. But my kind of thesis here is that we can't avoid the problem. Sensors are getting so cheap and so good that this combinatorics issue won't go away. Things are just going to get bigger and better. We need to figure out a way to solve that. So, kind of as Satya was saying before, we need to take a more holistic view of sensor systems, where we don't really daisy chain these things. We don't do them one at a time, but we actually include as much data as we can into the process initially, to make sure that we're incorporating as much as we can. So, this can be a Lidar stream, a camera stream for sure, but it can also be GPS data. It could also be supplementary sensor system data, where we know that it will inform these other things through time, which we couldn't do with our daisy chain processes, right? And most importantly, at the end of this process, we need to make sure that our calibration is presented to us with uncertainty. This seems counterintuitive because you'd want to be as certain as possible, but actually the processes we had before were giving us half truths. It wasn't lying, but it wasn't telling you how certain it really was. It was just saying this is right. That certainty can actually be a super powerful tool later on, when we get strange data points. We're like, how does this fit? Well, our calibration was so uncertain that if we deviate a little bit over here, now this works. Right. And we can figure that out for our whole sensor system.
Yeah, and if you take a very simple step of the calibration process, right? Let's say you're calibrating using a checkerboard pattern, then there is uncertainty in the determination of the corners also. We don't realize it, right? But there is uncertainty. Let's say you're using a slightly blurry image, then the corner was not detected properly, right? There is uncertainty how sharp the corner, where exactly the corner is located. And here we are not talking about pixel level accuracy. We are talking about sub-pixel level accuracy, right? So you need to know inside the pixel, where is the center or where is this corner? And if the image is slightly blurry, there is an uncertainty, and you can throw away that uncertainty and say, oh, we don't, this is the answer. But it turns out that if you actually keep that uncertainty later, when you're trying to do this global optimization, you can incorporate that uncertainty, saying that, oh, with this sensor, I was not certain about the focal length. And so if things don't match up properly, when I try to calibrate it in a global way, then I will penalize, I will actually consider this sensor, that this calibration that I had done, I would take the uncertainty into account. And so I will not weigh it as high. It's like voting, right? I'm not going to vote this person's suggestion of what its focal length is because the uncertainty is high, right? So we can think about it in those ways when all these systems also return uncertainty. When we are doing global optimization, we can take the uncertainties into account to do the optimization properly.
Mm-hmm. And again, I don't want to discredit those in the field. There are processes that do this right now, but they are relegated to academia for the most part. And the labs that are doing this research are fairly small. They don't have a lot of talent to go around. So the tools to do these things are currently restricted to those making products, unless you hire from the few groups that do this. So it is an urgent need in the field right now to have something like this. But thankfully, this problem has actually been tackled in the past, which I think is super fascinating, because as somebody who's been in this field for a while, it didn't really dawn on me until this year that these older techniques could be done in this way. But in my mind, the solution to this holistic view of calibration actually lies in bundle adjustment, which is nuts, right? Flexible bundle adjustment, I think, is the answer to this problem. It's crazy because bundle adjustment has been around in computer vision for a while. Bundles can refer to either the bundle of rays that come out of the camera center. So you can think of from a camera to an object as a ray, and you have a bunch of those. That's a bundle of rays. And then you figure out both the objects and the camera at the same time. That is a bundle as well. But really, bundle adjustment is just a way to put all of this into the same framework and solve it at the same time. The reason it's surprising is that bundle adjustment is used currently in computer vision mostly for camera data, like I said, but it can be extended to a ton of other data systems and sensors. Photogrammetry, if you're familiar with that field, or metrology, did this first. There are some bundle adjustment papers from the 1970s that go into this in incredible detail. But the things that they expand upon specifically are fascinating. So they don't just get the calibration parameters for your cameras. You don't just get the intrinsics and the extrinsics, but you actually understand the uncertainty and precision of those measurements. You understand the uncertainty and precision of your data put in. So what you were saying, the checkerboard corners, right? You would be able to solve for the checkerboard corner uncertainty as well. And you're able to take in the supplementary data. So if you had these GPS, marks that could help your camera positioning, you can effectively fold that in pain-free. It's fascinating that all of this was done so long ago. And computer vision employs these techniques, but not with the right rigor, at least in the tools that we use. So one of the things that I attribute that to is that computer vision was developed in a resource constrained time with a ton of data needed to process. And so when you're just thinking about these bundle adjustment operations, which are just basically huge matrices, thousands of numbers, right? And trying to do that at once, you effectively couldn't. So there were tons of shortcuts to get around that. But those shortcuts have been embedded into the engineering culture of computer vision to the point where the tools that we have now rely on them, which is detrimental.
Right. And just to, I mean, some of the viewers maybe beginners, and for their benefit, we can, we can think about a bundle adjustment problem as, let's say you're looking at this one point, right? And this one point in space, if you look at it from 3 different cameras, the rays from the 3 cameras, the lines that they would all intersect at this point, right? That's by construction that I'm looking at this point. But if you try to solve the reverse problem, you take 3 calibrated cameras and then you try to look at the same point from the 3 cameras. Let's say you take 2 cameras at a time, you can estimate the depth of that point. So you may get the depth at this location. Now you take the second the second pair of cameras, and it would not return the depth at exactly the same location because of all kinds of little problems, right? So the same point will not actually get to a single point when you take 2 cameras at a time. So you may actually end up with a ball of points. You have different estimates where this point can actually lie, right? And if you naively do it, you could say that, oh, take 2 cameras at a time and then simply average the results that you get for the depth of this point, and that's your real one. That actually will not produce very good results. It's an okay thing to do, but in real life, what you do is you try to solve the global optimization problem where all 3 cameras are involved. All 3 cameras are involved, and you try to find the estimate of this so that you minimize the error for all 3 cameras simultaneously. Not only that, you also question the intrinsic parameters of the camera and the extrinsic calibration between them, so that you try to find, you try to calibrate the parameters as well as the location of this point simultaneously, right? And that's what techniques like bundle adjustment allow you to do. Mm-hmm. And if you want to know more about it, people use the Ceres solver, which it's a very beautiful library for doing some of these things. It's an optimization library, but people use it for bundle adjustment a lot. You can try that out also. Mm-hmm. Yeah, they must have some examples in the documentation.
Yeah, I was about to say getting examples can be a little difficult because bundle adjustment is fairly complicated.
Yes.
Mathematically, but that was a great explanation. It's really boiling down, figuring out these uncertainties through the variables that you're provided. And for camera systems, that's the intrinsics and the extrinsics and the object space. And there are calibration methods that rely on this currently, which is why some people might be rolling their eyes at the suggestion. But having this holistically for 1 to n sensors for big machines is something I haven't seen yet. And I think even building on this mathematics could be a huge value add. Yeah. And that's a great segue, because there are some tools right now. I keep complaining about there aren't tools. There aren't tools. There actually are some tools trying to build upon this now. So LIOSAM is an open source, Lidar IMU structure from motion library. And what it actually does is continuously refine the Lidar and IMU calibration as it goes. So, using this continuous time model, kind of what the IMU relies upon, you can get better and better intrinsics or extrinsics for both of these things, which just refines your map. Amazing. It's super cool, but not a lot of libraries do this.
What does LIOSAM stand for? Is that an acronym?
I think it's Lidar Inertial Odometry.
Okay.
Structure something motion. I know the LioSam authors are just gonna spam me with hate mail now. But no, it's something about adometry.
Okay.
So, here, let's see. And then MRCal is actually a library. Let's see, from, what is it? Oh, now I'm going to get dunked on by MRCal too. But it optimizes the camera parameters and the object space points, which is the coolest thing. So if you go to the website, mrcal.secretsauce, they go into great detail about how this is done. So actually, if you want to get a start on bundle adjustment, I would point you to that page. They really do a good job of breaking it down. But what it does is, instead of just finding the camera parameters, it actually incorporates warp in your checkerboard. So Phil, we were talking about the checkerboard needing to be completely flat. If your checkerboard isn't completely flat, this system will tell you, this system will solve it and let you know, which is incredible. Again, this is one of the things that needs to be baked into these tools that is just now kind of emerging in industry. So, credit to these libraries. They're doing some good stuff. I actually think OpenCV has a checkerboard detector that incorporates uncertainty as well, but I haven't played with it yet. So kudos to there as well.
Yeah, I
like
don't know
the
100%.
MRCal website.
I'm not 100% sure.
It's why MRCal. It says, in essence, because all other tools are terrible if you care about accuracy.
Yeah, I mean, not to be too harsh, but I guess that's the whole point of the talk. It's the accuracy and precision is really where these things shine, and where the improvements need to be made. So, we're hitting up on time. I think just to close it off, really, surprise, Tangram is working on this. This is, we realize this is a problem because of our personal expertise. The entire team has gone through this pain, and the people we talk to have gone through this pain. And, people, friends of friends are panicking about the multitude of sensors that they now have to put on their robots and how they're going to deal with that. Like I keep saying, data perception pipelines are here to stay. They're going to be complicated. They're going to be rough. But solving this calibration idea from a holistic standpoint, really getting that software down, really understanding this from bundle adjustment and fundamentals will get us far. And so Tangram's excited to work on that problem.
That's great.
Please sign up for the SDK.
So will the SDK provide, so a lot of people, our listeners, they may be just vision engineers, right? They're just working with cameras. Will the SDK provide some easy ways to just calibrate multiple cameras? Is that, if I want to use only for cameras, right? I don't have a Lidar, I don't have other sensors, but I have 5 cameras, right? Is that something the SDK will also provide? Easy?
Yes.
Okay.
Yes, it will. Calibration is, we're focused on, plug and play sensors. We're focused on sensor pipelining, but calibration is first and foremost our priority. So whether you have a complicated system or a simple one, we want to make sure that that problem is solved.
Got it. And what kind of patterns are there? So there's the detector problem, right? Like we were working on a pattern called deltile recently, and deltile pattern it's a new pattern. It's triangular patterns instead of checkerboard pattern. So those kinds of things. Yeah, the idea is that triangular patterns, they have more stable points, and under certain conditions that's actually true. But my question was that would you have a set of patterns that you would support for this calibration, or how does it work?
Yeah, so we're actually working through that problem now. We're leaning towards Charuco and April tags, specifically because you can get good sub-pixel measurements. You can do some signal processing to understand that, but you can also see a part of the checkerboard and still get accurate metrics. This ID is really important.
Right.
yeah, so that's where we're leaning right now.
Will it be extensible in the sense that, oh, suppose I have my own pattern, can I write a detector so that now I can use all the tools you have, but I write my own detector so that I can add my own pattern now?
That's a great question. One of the most important things in our system is understanding the uncertainty. So, if you write your own detector, you're, taking that upon yourself, in a way.
So you have to write that piece.
That exactly, or at least admit that I don't know.
Right.
In which case, we'll take that into account. Right. Yeah.
But will it be extensible? Will people be able to write their own detectors as a plugin or something?
I can't promise that, although I like the idea. I mean, democratizing this is priority number one. That's the mission of the company. Right. But who knows? Yeah.
Cool.
Mm-hmm. So yeah, Sensors for your sensors, part 2. I know that was a lot. Yeah, but thank you.
Yeah, we are ready to take questions from people now.
Yeah, do we want to do trivia first?
Yeah, trivia. What's the question?
Will you tell them what they'll win, Satya? Right.
So the person who answers the question first, and by first we mean whatever shows up on Phil's computer, because I'm not 100% sure, how these systems work, whether it will always show up correctly on everybody's computer. So whoever shows with the right answer on Phil's screen will get an Oak One for free. And so that's the giveaway. And OpenCV AI Kit is basically a smart camera, which allows you to do neural inference on the device itself. So it will run a neural network on the device. It's fully programmable, and it's been very popular with our users. So
yeah,
that's
definitely
the win.
Awesome prize. So Brandon, would you mind unsharing your screen for the Q&A part and trivia here? Awesome, thank you. So earlier in the presentation, Brandon described what we colloquially call the calibration dance. What is the more official name for this method?
It's already there.
Looks like P. Sharma was the first one on my screen here. Very, very quick. Didn't even finish saying it. So we'll get in touch with you after the webinar to figure out how to get you your free Oak One.
Well done. That's so funny.
So just for historical reference, Zhang from Microsoft, he invented this method, and it was in MATLAB. One of the things there are two things actually, which people, initial adopters of OpenCV used. The first one was for face detection. OpenCV was very popular for face detection because at that time, real-time face detection was something that you couldn't find implementations of it, and OpenCV had one. And the other one was camera calibration. This method was really good.
Yeah. So I guess we'll move on to Q&A here. First of all, I have, I'm an agent of chaos. So sure. I'd like to ask Brandon and Stia both, do you have any tales of calibration gone horribly wrong for the audience?
Oh, I have a lot of tales of panic. So yeah, I guess one of the, I worked on, the structure core, which was the new version of the occipital structure sensor. And one of the coolest things with that machine was understanding the stereo pair, because there are two cameras here. And if you, have the rotation off a little bit, it can go out. We are getting urgent, I guess this isn't a calibration problem. We were getting urgent feedback from our factory saying, things are bad, like calibrations aren't working at all. And so once we actually understood the problem, it was that somebody had just removed the target. It was just gone. And so like the process of actually trying to understand this was pointless because it was getting like crazy mathematics and everything was wrong. So it was saying my eyes were like this. And I was like, oh, I can't find anything. It's like, well, no, of course, come on. So data is important, I think, is the rule there. Yeah.
That's tremendous. Thanks for that.
There's another story. It's not a calibration story, but it's a fascinating story about the 1966 World Cup finals, where they were playing England versus Germany, and there was a goal scored, and an English researcher proved that that actual goal was not a goal, and he got so much hate mail based on multiple camera footage.
Oh
right?
my God.
But he did it much later, right? This 1966 goal, this happened, but then later when they wanted to analyze, when the things cooled down many years, like decades later, he did this analysis and showed that it was not a goal based on the footage they had, multiple cameras, right? He got so much hate mail because he was saying what the Germans were saying. I have actually on my blog, I have this story. Find maybe soccer. If you'll search for soccer on learnopencv.com, you will see that story.
Yeah, people take their football very seriously over there.
Right. And they will love you for saying football.
I know. I had to sneak that in there. I'm trying to turn babyface here. So a lot of people have asked about where this will be uploaded. This will be put on our YouTube channel. I'll drop the link in the chat here in a minute. This, as well as every other episode, goes on the OpenCV YouTube channel, which I'll drop the link for shortly. A couple people asked as well about where the slides for this will be. The slides are already uploaded on tangramvision.com's blog, which I'll link to in the chat now. Somebody asked, several people asked about OpenCV, the library, kind of more generally. One of those questions I think is a good one to answer here, Satya, which was, what are the contributions that OpenCV is looking for the most right now?
Oh, well, this
is what's the best way to contribute if they want to do code for OpenCV?
It's not really code. There is something that is very close to my heart, but we have not been able to put a lot of energy into it, and that is packaging. So, when people want to build OpenCV from source, especially for Raspberry Pi and other things, it is a nightmare, right? It will take you 2 hours to do that. And what I want, and we have started doing this, we have started working on NuGet. We want package managers, right? We want, packages for different platforms, which are precompiled binaries so that people can simply install very quickly. So that's the biggest place to contribute. We are actively thinking about a project which will accomplish this, but it's in early stages right now. We just started with the NuGet package. It's Google Summer of Code project. And then at Learn OpenCV, we developed an internal, installer for Windows also, but we need to do it for all the platforms. That's the biggest on my mind.
Great, thanks for that. Somebody asked about satellite sensors and geolocation data. We didn't really talk about that. Brandon, does Tangram have a plan for incorporating geodata as well with these calibrations of sensors?
Yeah, so using GPS, GNSS is actually a pretty common requirement for a lot of people we talk to. The tricky part there is there are many protocols for doing such. So it's not a matter of, are we going to do it? We absolutely are. I think it's just a matter of what the priority lies, where the priorities lie there. Does it, is it mostly for time synchronization, which is huge for GPS? Is it mostly for spatial data? What protocol are you using? These are things we're still kind of learning through the SDK alpha. And we're going to apply those learnings later on. But yeah, absolutely. It's something we absolutely plan to do.
Several people have also, thanks for that. Several people have also asked about, understandably, OpenCV AI Kit and the Tangram SDK. Is that is there a plan for that? Is it already supported? People want to fuse multiple oaks together and stuff like that.
Yeah, we're hoping that the Tangram SDK is low enough level where these things can just plug in seamlessly. because at the end of the day, we're all about making the data pipeline work well. And once the data's out, you do what you do. So we absolutely, if we can hook into an OpenCV pipeline, that'd be great.
Awesome. Yeah. If people want to contact you, Brandon, and ask you questions about the horrible lies you've told during this webinar,
absolutely.
How can they best contact you? Where they find you?
You can DM me on Twitter, dminertx. I'm usually there. That's probably the best way. And then or LinkedIn, absolutely.
Cool. And also regarding timeline, like how often what's the timeline for inviting people to the Tangram SDK alpha, etc.?
Yeah, great question. So we actually just brought on our first cohort a couple of weeks ago. We're looking for members for the second cohort now. So absolutely, if you have a vision-enabled device or product that you would like to try out our SDK on, come on down. Go to tangramvision.com, put in your name.
Great. Appreciate that. We're hitting up on time. You want to take us home, Satya?
Yeah, thank you everybody for showing up on this webinar. I really enjoy these Thursday webinars because we get to talk to some people, fantastic people like Brandon Miner, who educate us on various topics, and it's usually on very different topics, right? And we also get to communicate with OpenCV users, and it's just fascinating. So thank you so much. Thank you, Brandon. And as always, thank you, Phil.
Yeah, thanks for coming, everybody. As always, we will see you next Thursday, 9 a.m. sharp. Thanks for having me.
Bye.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by ModelPlace.ai, the AI model marketplace by OpenCV. Learn more at modelplace.ai.